and the active diaphragm is going downward, then the stabilizing diaphragm is going upward. And the first thing that appears here is a kind of a negative feedback, which apparently is what's controlling the phase relationship and the flatness of the phase response, which I'll show you in a little bit.
Hey everybody, Dave Lindberg in Hong Kong with a new episode of THD Podcast. Thanks for joining us. Today we have a company we've had on before, Dinaburg Technologies. Previously we were talking about something big, but now they've miniaturized it down to a headphone-sized driver, and it's making some big impressions. And some of those impressions happened at the Alti exhibit, one of our sponsors. So give a shout out to Alti here. So a lot of people were really impressed with what Dinaburg did at the high-end show in Munich. So we encourage people to talk to Barry and join the Alti Association, as we think it's a great organization for audio networking. And also Audio Express, please check out their publication. There's some articles that you can look historically on Dinaburg to find out more if you find what we're talking about today interesting. So without delay, let's get into it. Let's go diagonally. We got Simon Weston in Sendai, Japan, up late. Thank you, Simon.
Thank you too. And we've got your night view this time. We don't often see that. My one's always the same. But...
Yeah, I try to keep it fresh. And we've got Simon Dinaburg, the CEO and founder of Dinaburg Technology. Good morning, Simon.
Good morning, gentlemen. Good afternoon.
And Jim Tuomy on the East Coast, also with Dinaburg. Good later morning, Jim.
And morning to you as well. Or wait, evening or early morning or something, whatever. I can't keep track.
It's almost 9 p.m. here in Hong Kong, 10 o'clock in Japan. So yeah, we're covering the globe here today. So yeah, Simon, thanks for coming back on the show. We've been hearing about some progress with your headphone space, and there's been some technology improvements that you've been trying to define. So I think a lot of what we're going to talk about today is explaining perhaps a bit of what we know, what's going on with these C2S headphone drivers. So maybe you want to make introduction, and then we'll let Jim run through a presentation for us.
Sounds good. Dave, Simon, thank you for having Dinaburg Technology back on the podcast. During our last conversation, we discussed what makes C2S work in general. Today, we would like to discuss the C2S headphone reference design we've been working on for the last couple of years. As you mentioned, we released it during the Munich show, and we had a phenomenal feedback from industry peers and from some of the potential consumers. And today, we would like to introduce you to Jim Tuomy, who was instrumental in the last couple of years to help us to understand and discover all of the benefits of the C2S design in headphone application. And Jim possesses extended knowledge in acoustic design engineering and digital signal processing. And I will pass the mic to him. This way he can dive into the conversations, less presentation.
Okay. So this is the C2S headphone reference design. It should be pointed out that C2S works in all kinds of sizes, but it has some particular advantages in headphone work that are a little bit hard to see on the surface. So I've got a little presentation to show you what's going on with it. This is a bit of my background, is no biggie, but I've been around audio a long time and hold a few patents, etc. So the background of the concentric coplanar stabilizer is that there is a center. For one thing, what this does is produce a lot lower distortion, much better phase linearity than you would expect, and much more manageable group delay. So as I said, it works no matter what size it is, but this is a picture of the actual headphone driver that we've been using, putting in demo units and exemplar product type stuff, and also testing a lot. So as you can see, it has a sort of an active center area that is the driver that's connected to an amplifier. So it's moving under power. And because it's moving in a closed acoustic case, it causes the outer ring here, which is basically a form of passive radiator called the stabilizer. It moves it in the opposite direction from the main active diaphragm. So to show you a little, drawing of the whole thing, the active center diaphragm goes both up and down, of course. So it's a bidirectional, and in one direction, the bottom direction, it has a reflective surface, or you can say a pressure container under it. So we just call these the active and stabilizing sections. So the active's in the middle, the stabilizing section is in the outside. And so what happened, and by the way, if you guys have any comments or questions, I'd appreciate them. So anytime, just shout out.
Okay.
The stabilizing diaphragm moves in the opposite direction from the active, from the bottom of the active diaphragm. So the active diaphragm is going downward, then the stabilizing diaphragm is going upward. And the first thing that appears here is a kind of a negative feedback, which apparently is what's controlling the phase relationship and the flatness of the phase response, which I'll show you in a little bit. But in any case, it then also acts as a classical passive radiator, where in lower frequencies it behaves as if it's a passive radiator, but it's in phase because it's concentric. It's a very strange alignment, but it really works better than you'd expect, as you'll see from some measurements coming up. So we wanted to kind of break down the benefits of the application, starting with gaming, which is really one of the most demanding things. This is a family of curves that's been adjusted to just pay attention to level linearity and loudness. So as you can see, we limited this at 110 dB, which of course you'd do in any kind of product. Probably limited in time as well as in level, so that it only hit 110 in very, very short intervals. Or anyway, but the point is that these are very linear level wise, and as you can see, there's no compression at all at 110, so it can get quite loud. Then this is from the phase response measurements that are all of those same levels. So it's a whole bunch of channels superimposed. And as you can see, the phase linearity is, in this particular case, extremely good. And also doesn't change at all for level. So it stays the same. Now, this is important for a simple reason. When we're hearing something and we're trying to locate it, the actual tight location from a distant source is not level difference from ear to ear. It's time difference, interaural time difference. So the fact is that it's been proven time and time again that people can locate objects in the distance with a response that is not sinusoidal. Okay, so as a sine wave, we flatten out at 20 kilohertz if you're a young lady. If you're anybody else, you don't get to 20 kilohertz. But if you think just of what is the equivalent time that you have to differentiate in order to locate that distant threat that might be a long way off at night or whatever, it comes close to a microsecond. So you have to have a response, the ability to detect interaural time difference down to in the vicinity of a megahertz, a microsecond, in order to do this location. So that means that the phase linearity, especially in headphones, is utterly critical for location cues and 3D, the feeling of 3D, and particularly in order to hold the phase together enough so that you will get a sense of the sound lifting in the middle. This is because, this happens not to everybody, but to a lot of people, because in the sense of your hearing, the reflections that you get off your body and all of that other stuff, you only hear something exactly evenly in time between your two ears when it's above you. Otherwise, you're getting all kinds of reflections and so forth. So the tendency that we found out when I was doing Phasics, which was a studio monitor company. The tendency is the better phase you get, the more you will also get a lift in the middle, and that absolutely shows up in the Dinaburg headphone. So
Hey,
anyway,
James, can I just ask, what measurement condition is used to generate those responses in the
yeah,
phase?
this one was a little bit odd. I just had a flat plate, right? Just a plexiglass plate with a 50 kilohertz flat to 50 kilohertz microphone, and the audio precision system. And that one, it really surprised me, because normally it doesn't come out that flatly. There's generally a big lifting curve there, but I put this up because it was the curve that I got
Just,
at the time. I checked for
just
error.
maybe jump back to show people the slide while we're talking about it.
Let me see if I can. Let me see if I can find the.
Just go
This is
backwards.
actually a good catch. Now I have to find the place where. Oh, there it is. Let's see the. This is a little hard to control. There we go. All right. So this is too flat. You would expect this to lift over here on the right hand side much more than it is doing. But as you can see, that the parameters I put in were 30 hertz to 15 kilohertz, and this is what it spit out at me. And I was really quite surprised. But I figured, well, I'll publish it because it was real, and it was there. So it is much more common for me to get a much bigger lift here, and for me to get a much larger amount of phase shifts. So very possibly I should pull this one out of here and replace it with something that is more common. But the reason that I wanted to put it on was it was a combination of all of the levels that you saw in the previous. These exact levels. So it was during the same test, right? The same moment of testing on the AP, and that's why I put it there. Anyway, in a minute, I'll show you phase responses that are more normal. And honestly, now that you've mentioned it, Simon, I agree. I should probably pull that out of there. Anyway.
Well, and part of the intent, I suppose, is trying to eliminate some of the variables from it too. So you don't want to see what the coupler's doing. You want to see what the headphone's doing.
Yeah, right. And so, listen, this is the reason for my headphone testing. For anything regarding compliance, of course, and safety, I'm trying to use the standard, ear thingy, the ear connection stuff that is, critical to that. But otherwise, I prefer to use a flat plate with the headphone just squished against a plexiglass plate. And this is also AP feels the same way. And then it's really, really hard to test a headphone when you're also going to try to voice it, right? It's not so hard to test it for frequency response and so forth. But when you're trying to voice it, flat plate is the way. And this was done with a flat plate. So all I can tell you is that it was real. So let me move on to some of the other stuff. This haptics is, we are asked to talk about haptics because it's become more and more and more important. Well, the thing in a recent haptic project that I had, one of the big deals was to try to locate sounds that would also be a physical vibration, right? So you wanted to locate it, let the listener locate it along with the physical vibration. And that was kind of hard to do, but it turns out to really enhance the whole feeling of the cues, the acoustic. If you give a person some acoustic cues to match the vibrational cues, it really helps the experience from my research. Anyway, the other thing was active noise canceling, which, Simon, I understand is a major section of what you do in life. So here's just, I just put together the usual block diagram of the feedback type of noise canceling, and point out that there is often a phase correction network consisting of a whole bunch of little LRC sections, inductive, resistive, capacitive sections that have to be adjusted with a great deal of pain. And like other headphones that I've worked with, where there are two drivers that are concentric, the Dinaburg C2S alignment doesn't really need one at all, mostly because it's so smooth. So here's a much more ordinary looking phase, response diagram. This was done at a later time. And as you can see, it's much more following the ordinary, usual pattern of phase response. But as you can also see, this is, I didn't filter this at all, or make a version that squished any peaks or changes. So as you can see, it's a very smooth response. There's nothing unpredictable here, particularly if you're only interested in doing the noise canceling to a little over a kilohertz, which is the usual for feedback noise canceling. So this means it's not only sounds better, but it's a lot easier to deal with because you have to put less corrective networks in the negative feedback that happens for ANC. So another thing that people don't generally think about is that when you're canceling noise, particularly in the very low frequencies, you need to do it with a lot of power. So if you're in an aircraft that is a noisy aircraft, a noisy jet, meaning not a private aircraft that has all kinds of sound canceling stuff, you're going to need to do some ANC at some very low frequencies. And the ability to do up to 115 dB without any sort of compression and without any kind of severe distortion means that you can cancel much louder noises than you would ordinarily be able to cancel, in my experience. Now, we haven't yet come up with a full mock-up of a noise canceling version of this headphone, but we've got some demo boards from Analog Devices that will help us do just that. So in the next month or so, probably have something that actually shows some noise canceling results. And let's go on to the next one. This is the THD at 100 dB SPL, just to show you that the THD is fairly low. Starts out at about 3%. This was from 50 to all the way up, and falls pretty quickly to under 0.1%. So this is in my opinion, this is an effect of that negative feedback effect that I was showing you before. And I wanted to mention here that feed forward ANC has very similar requirements for phase linearity, loudness, and distortion. But as most people know that are involved in this stuff, feed forward is a whole nother different beast from feedback. So let's see. So the next thing we wanted to talk about was deep bass response. And again, this is just the last five curves in that last graph I showed you. The idea is you can get down below 50 hertz to well over 110, probably 112, 114 dB before you start to hit compression. And so you're never going to actually get that to somebody's ears, but because it's too loud. But on the other hand, it means that you can produce bass that's very smooth sounding, very low distortion, and behaves as people want it to, who love deep bass. So, and the last thing is we're just kind of summarizing the thing, just to say it's easier to do ANC, and I didn't really hit this too much, but another thing about phase that's really important is we developed our hearing in caves. Okay, so we have a whole bunch of stuff that stops reflections from happening below a certain amount of time. And one of my the patent I'm most proud of is one that talks about how you can use a self-reflecting, self-diffusing case for a speaker to make it so that you don't get confused by reflections. But in any case, the point of all of this is to say our ability to understand what someone else is saying is very highly dependent on our ability to differentiate between reflection and direct. And that's highly dependent on phase and timing. So the whole business about being really tight timing and really low distortion is it means that you get a much better feeling about listening to someone speak. So you enjoy movies a lot more because the people who make movies spend more time on dialogue than most people could ever imagine. And the automatic dialogue replacement world and also the whole business of doing Foley effects, making footsteps audible, all of that stuff is phase critical. It's terribly critical. And that means that listening to a movie through these things is really nice.
Yeah, I mean, the biggest buzzword going in audio is spatial right now. So
yeah. Well, and what people forget is that spatial means getting everything right. And many years ago, when Dolby was first doing things, they suddenly realized they had no chance of getting a stereo a presentation to have the sort of phantom center that stereo can have in a good room with good speakers, la la la. So they had to put in a dialogue speaker, a center speaker, because there was no hope of doing anything else. They tried. It wouldn't work.
So is it historical that Dolby was the one that introduced the center channel in home cinema?
Oh, absolutely. Oh, okay. Absolutely. Well, look, Dynaco, everybody borrows from everybody else.
Yeah.
And the guy who started Dynaco invented almost all of Dolby, but Dolby knew what to do with it. So that the whole original Dolby surround is based on stereo and figuring out how to pull the image out of a stereo. Well, that was Dynaco that did that.
Okay.
And then Dolby pulled it out. But then they realized that without a center channel, what could they do? So they dropped the center channel in it, right? That Dynaco did not do. They did it because, see, Dolby went out to all the theaters and actually tried it and, made it work. So then Dolby Digital was a combination of figuring out where to put it in the film, where to put the audio signal in the films, the actual film strip that was going through the projectors, and also how to do it digitally. So in any case, the point is that they had to force a lot of what we think of as surround had to be forced to match theaters, which were built in malls. They're just concrete walls. With the Dolby spec is, about 4 inches of cloth separated from a concrete wall with a little stuffing in between. So the acoustic, they're in terrible shape.
So is there any going back from because Dolby kind of owns the content of the imaging, right? So is there any going back to having speakers that are perfect phase and then you wouldn't need that center channel?
The trouble is you could do that, and people have tried. I mean, DTS among them. But the problem is that the problem is not the speakers. It's the acoustics of the presentation space.
I see.
Right?
It provides some guide rails. Right.
That's what makes it impossible. Otherwise, it would be possible, or intriguingly, outdoors, it's possible. Right. So in the U.S., particularly on the West Coast and in the South of the U.S., there is a trend toward having nighttime theaters outdoors on pleasant nights, and so forth. So it's actually, except for the power problems, it's actually much easier to hold a really contiguous signal outside than it is inside. But in any case, there's been the whole business of Dolby's elevation channels. That was all about the proscenium stuff, that most of which was figured out by David Griesinger, who was the chief engineer for uh, for all kinds of people, but Harman at one point. Um, and Griesinger went through every opera hall in the world and went. He hated movies, but he loved opera. So he worked out all of the things that could happen in a room. And a
Mm-hmm.
lot of those turned up ultimately, as they filtered through the audio world, they turned up into Dolby Atmos because that started to handle the proscenium, the whole business of elevation, the whole business of the fact that Griesinger found out that the way you hear bass is partly affected by the elevation stuff. It's not the bass in other words, it's not in bass frequencies, but rather the bass can be enhanced by having elevation stuff. So Atmos and its elevation is going to be responsible for much more accurate playback in both living rooms and movie theaters, in my opinion, because now with elevation, you kind of forget the acoustic space you're actually in. It's all about kidding your brain, which
Mm-hmm.
knows perfectly well what a hall sounds like,
All right.
right? Versus the movie.
Okay.
Um, it's
But
all about kidding your brain to believe what the movie is saying rather than what the hall is telling you.
all right. So speaking of hitting your brain, Simon, do you have Weston? Do you have any questions about how they
Right
supply?
back, yeah, right back at the beginning, you showed us a diagram of the speaker with the size, and it was like 70 by 60 millimeters, something
It's
like that.
60 by 72 millimeters overall, OD.
60 by 72. So that design is actually for an over-the-ear headphone, and that occupies your whole baffle
That's right.
plate,
Yes.
essentially.
Yes.
Yeah.
Yeah.
So
Correct.
then with this design, like in most common headphones, you'll put a ring of holes or some venting with filter paper on top of it. You don't do that in this case?
You're talking
No,
about in the
well,
back of the driver?
On the baffle plate between the front and rear cavities.
the thing is that all of the acoustic science that should be applied to this has not really been done yet. Okay, so it's this is one of the drivers that I put into a plate to test it, right? And the thing is that there there's all kinds of stuff that hasn't been tried yet because it's a little different, right? So what you're saying, first of all, needs to be approached and done. It needs to be developed, but we haven't done that. All we've done, or I should say, in this case, all I've done is to take the driver, itself, and having had the manufacturers put it in a headphone can, so it has a back volume, etc. I just, brought it up to the point where we could straighten out its frequency response using just ordinary, normal Sigma Studio DSP, and then go from there in terms of saying, okay, this is something you could do. We have not put it in the hands of a headphone acoustic specialist, which is kind of the next step that should happen. But all of that, but and in particular, the thing that I've found out in when I've been working on developing headphones is that the ear cushion is perhaps as important, or in some cases more important than the driver itself in terms of both the extreme highs and extreme lows. So rather than to try to do that, because Dinaburg isn't selling headphones, we're selling a driver. Rather than to try to do that, it is our hope that this will get into the hands of people who can do that kind of that improvement in sophistication and so forth.
Mm-hmm.
So and then furthermore, it should be possible to make really small versions of this too, but we haven't gone to the microscopic side of it either. The side that would be something that fits in your ear.
And in this test case, the rear volume is a sealed volume.
That's right. Yes, it's sealed. Well, in the general approach that Dinaburg took with this, and the patent itself, it always speaks of a sealed back volume in terms of something that is a producible item. The effect, what I was talking about, the kind of negative feedback effect, is described in the patent as being a reflective plate, even in open air. Right, so that's a part of the patent, but it's unlikely that a product could be developed with that for the simple reason that it's impossible to get much bass from this kind of driver when it's in open air, when it's not. So that passive, the radiator that is the not compensating,
Stabilizer.
stabilizing diaphragm, it is critical that it can act as for lower frequencies, that it can behave as a passive radiator as well. And without that, you don't get the low frequency response that is really very good. I mean, you can think of this as like a regular speaker that has a passive radiator subwoofer attached in one part of the way you can approach it. That's not the part where there's feedback and phase correction and so forth. That's more like if you could think of the passive radiator as having a sort of a phantom crossover, right, where the active radiator is contributing less and less to the bass, and the stabilizing radiator is contributing more and more. At that point, the stabilizing radiator begins to behave as if it were a passive radiator subwoofer. Right.
Okay, so at very low frequency, its motion is in phase with the speaker diaphragm.
Weirdly, yes, apparently so. And that's another thing that really needs to be looked into. Those phase things that I was just showing you, that second phase diagram with the, if this was just a plain old fat passive radiator, you'd have a big bump, a big, weirdness around where it was switching from active to passive, right? But it doesn't. And the negative feedback part of it is the only way I know of that could happen. But it's not been fully researched at this point. That part of it, that aspect of it. We know it works. We know the patent works and so forth. But the math has not been done out, right?
Okay. And then in the higher frequencies, it's largely moving out of phase with the speaker diaphragm.
That is right. But it's contributing very little to the total output at high frequencies because it's not moving because it has a mass, right? Just like a passive radiator, it has a mass, and its suspension, its mass, and the air that it's moving in form the whole spring mass thing.
Right. So it's relatively massive. The
relatively, yes, relatively. Again, you have to think of it as think of it like as if it were a passive radiator subwoofer. Right. In which case the passive radiator is quite massive, right? And has very little response above low frequencies.
Yeah.
And that's the way this is acting too. So it kind of disappears at, I'd say, I'm guessing here, 300-ish, 300 hertz-ish, just goes away. It's not there.
In that sense, its own mass is creating a crossover transition region.
Right. You can think of it that way, and I believe it should be thought of that way. Yeah. It's there's a lot more to be done in terms of, as I was saying, in the mathematical sense, to really figure it out in terms of the amount of the exact prediction of behavior. In other words, to model this mathematically, right? There's more to be done, right? There have been quite a few successful attempts to model it in the multi-physics packages, and that has worked very well to give us an idea of what's going on. But what we need is the kind of simpler model that you could do on the back of an envelope. You know what I'm saying? That you could do without deep knowledge of the multi-physics packages that can do these things. As you know, that's a pretty high specialty.
So using the term a stabilizer ring, what is it stabilizing?
Well, the thing is that then in the original patent, remember we're crossing a language too, but in the original patent, I think that you could think of the way this works that I can see is when you send negative feedback into a noise canceling system, right? When you turn it on, the bass flattens, as you know, the phase straightens out, the distortion comes down. All these things happen when you freeze and unfreeze that stabilizing diaphragm. So in the vicinity of what you could think of as the crossover, where both the drivers are working, there is a negative feedback action happening that ends up making it quite phase straight. This as I was saying earlier, I didn't want to get too far into this because I can't describe it mathematically yet, right? So, I know it's happening because I can see it, I can measure it, I can show it, but I can't come up with the exact relationship yet.
And then as far as the electronic side is concerned, it's still a 32 ohm nominal impedance speaker.
Yes,
Yeah.
that's right.
18.
18, yeah, okay.
18 ohm. This specific
Okay.
unit is 18 ohm.
Okay.
So it's, I mean, obviously it can be wound to anything. That's just what you decide it should be wound to. So this group of samples is somewhat lower. But again, where it's going to be used in ANC applications, that's important to match to the amplifier and all that business, but not critical in a sample unit like this. So anyway, that was the feeling.
And has there been some kind of extensive secret process in terms of developing the right mass and stiffness?
Simon has been involved more with that with the manufacturers, and I'm assuming there is because they keep getting better.
Like everything else, trial and error. You go through the process to figure out. It's like Jim said, we kind of break into conventional thinking to some degree. There is no right formula for what works for us because it's typically designed for a traditional, what you would call transducer with the passive radiator. We do not have a radiator. We have a stabilizer, pretty much that physics skewed a little bit. It's a little bit unconventional, but to some degree, you still follow the same standard audio product design. And as you try and you experiment, you're figuring out what works better. And we're on a Gen 2, the headphone driver at this point, and it is every generation, it gets better and better like any other product supposed to be. And the proof is in the pudding. When the demo gets experienced by the end customers, they have all the same kind of aha effect, experience.
It's really clean sounding, really, really, really clean sounding, surprisingly so. I think the thing to do is to think of the crossover region. You know how if you cross over two drivers, then the critical stuff, the part that's going to kill you, is where they're merging, right? So the crossover region between the two drivers. I think that crossover region is where this feedback action happens, and that's what I'm striving to define accurately and so forth and so on. But my firm belief, because I've seen this too many times, there's a thing that people, audiophiles say that noise canceling, makes the sound worse. In my opinion, it does the opposite, at least the noise canceling that is feedback based is likely to make the sound a lot better. The noise canceling that is feed forward based is likely to hurt you because of the fact that it can behave as if there's a lot of intermodulation, distortion, and so forth. But if you just think about feedback, it tends to improve the performance of the transducer. And that's kind of, Simon, it's kind of interesting that I'm interested to see what you think because you've had a lot of experience in the ANC world. And basically, I'm basing a lot of what I think on what happens when you apply ANC of the negative feedback kind.
Yeah, well, absolutely. That's the key point, a negative feedback system. So you are inherently going to reduce distortion, provided everything is clean and tight.
Right.
But you still do have talking of crossover region, you still have a region whereby your effect diminishes and you can have amplification.
Yeah, absolutely.
But if you can manage that, then no, you should end up with a better audio performance.
So this is my belief of why this thing works. I'm very fond of telling all of my customers, look, whatever you do, you can do miracles with DSP, but you can never reduce distortion, right? Not with DSP. You can reduce distortion in a giant way with negative feedback, right? And that's what I believe is happening here. I've become convinced of it. So, as you say, the rest of it, when this effect falls out, interestingly, it falls out in a place that's by the time I'd say 2 kilohertz or so you've reached 2 kilohertz. There's probably not much of the negative feedback, but a lot of what you need from it is phase correction at what you could say was mid bass or high bass or something in the 100 hertz area, 150, 200 hertz area. That's where dialogue sounds so much better through these things. It really is remarkable. So, our feeling has been that another thing is that the intelligibility goes up a lot. So there are probably some pretty good military applications. Because, as you know, the whole thing with military headphones is that you are always on the edge of intelligibility. You are always almost dead in the water for intelligibility. So, so any tiny improvement, even a few dB, would be very well worth it. Anyway, so I'm always interested in your opinion, though, Simon. So, because
I don't know which Simon he's talking to.
I'm talking to you. I'm talking to the headphone expert, Simon, the ANC expert, Simon. Golly, we should have come up with another name here, Simon 2 or something. But
All
anyway,
I think,
really think that that's an important part of it.
okay. No, but I think that's a pretty good dive into what these 60 by 72 drivers will do, at least a preliminary level for headphones. Maybe we'll double back in a year's time to see where we're at with ANC and whatever else you get into. But if Simon Weston has no more questions, we'll table this for today.
I do just one last thing, because I just wonder. I'm just curious because this type of system design is there may be some possibility where in fact it's compensating for variations in different volumes that you have in the front and the rear, so that inherently provides a different stiffness, and you kind of end up.
Now that's really interesting, where you start to see it as a fourth order bandpass. Is that what you're thinking? You're getting into that realm?
It's something along those lines, yeah.
Yeah. I'm not saying exactly. I'm just saying you begin to think of it as a bandpass. Oh yeah. Now that's where it gets really intriguing. And yes, that has occurred to me. Again, it's as you can well imagine, getting into the area that's been so well documented for so many years in audio and doing something new, you're faced with a very daunting task in to try to define that kind of thing. But you're right. I think you're absolutely right. That's where some things are happening here that need definition. And will have definition particularly as we get deeper into the ANC stuff, and into the business of defining the feed forward type stuff, because now you're talking about what happens out versus inside. The whole system of the headphone. So I'm very intrigued to find out more stuff, and of course we'll keep you posted as we do.
Thanks for your patience, Dave.
Oh, no worries. We're
sorry about the deep, the rabbit holes.
No. This is all good stuff, and
I can tell you that there are not many people in the world that I can talk this over with. So I'm really happy to have some people that I can talk it over with.
Anytime.
Cool. All right. Well, people can find out more. We'll put the links for Dinaburg below, and people can check out that stuff there. And so, Jim and Simon Dinaburg, thanks for joining us this morning, this evening, wherever people watching are. And people like, subscribe, share, all that good stuff. It really helps out the show. And we'll see everybody on the next episode. Thanks, everybody. Bye-bye.